3.4, that's where we're at. We looked at the second derivative on Friday, and we discussed what information that second derivative gave us regarding the graph of the original function f. And the answer to that question is what? The second derivative sine tells us the what of the curve? Concavity, okay, also known as curvature. And if a graph is concave up, like a cup, its second derivative will be positive and vice versa. Bless you. And if a second derivative is negative on an interval, then the graph will be concave down like a frown. And of course, if the second derivative is 0 on an interval, it'll be linear. Okay. So if you know the sign of the first and second derivative on any given interval, then the graph is going to look like any one of these four segments from the circle. Okay. So if you then combine that with the f values, the function values, you can then place that shape on the coordinate grid in the right spot, and you know exactly what the curve is doing. Okay. We also explored one other idea, the relation of the tangent and secant lines based upon the curvature. And let's review that very quickly. If you have a graph that is concave down like a frown, doesn't matter if it's increasing concave down or decreasing concave down, the tangent lines are going to be above the curve and the secant lines are going to be below the curve, opposite sides, based upon the concavity. And if the graph is concave up like a cup, whether it's decreasing concave up or increasing concave up, then it's the opposite. The tangent lines are below the curve and the secant lines are above. That's going to be a little bit more important when we get to approximations using tangent lines. Just something to observe right now. Okay, so now we're interested, just like we were for first derivatives, where can we have local extrema? Well, we can have local extrema at critical values, and that's where the first derivative is 0 undefined. We now want to know at what values of x can our function change its curvature. Where can it go from concave up to concave down? Well, good question. We're going to define it to be an inflection value. At any x value p, instead of x equals c for a critical value, that's in the domain of the function. That's important. It's got to be defined there. F is said to, bless you, f is said to be an inflection value of the function f of x if the graph of f of x changes from either concave up to concave down, or vice versa, from concave down to concave up. So that's it. As long as the function is defined there, and the graph goes from concave up to concave down, or concave down to concave up, it will be an inflection value. That is, now here's the important part. Let's say you have a function that goes like this, and goes like that. Notice to the left of that dot, I put a curve that is concave what? Up, so the second derivative is positive or negative on this interval? Positive. To the right of that dot, I drew it concave down, so the second derivative would be negative. Assuming that the curvature changes through a continuum to go from a second, let me keep that thinner. To go from a second derivative that is positive to a second derivative that is negative through a continuum, it must pass through what value? 0. Yeah. So at this point right here, at that point, not on an interval, the second derivative equals 0. Okay? Just like at a local max or a local min, the value of the first derivative at the high point is 0, but the sign is a positive or negative on either side. Same thing with an inflection value. It's going to be where the second derivative equals 0 and the sign of the second derivative changes on either side. But there's another place where it can happen. Okay? We call the y value combined with the x value an inflection point. So if it just asks you for the inflection value, that's the x value. If it asks you for the inflection point, that's going to be the x and y value. Now, here's another important note, very similar to a first derivative note. A graph of any function can also change its concavity, not just at an inflection value, which is in the domain of the function, but also at a discontinuity, like a vertical asymptote. So could a vertical asymptote be a critical value if the function wasn't defined there? No. Okay. Same thing here with curvature change. If you have a vertical asymptote, it's going to make its way into the number line chart when you're testing intervals of concavity, but you're not going to call it an inflection value. Okay. Here's some examples. Like I said, here's a graph that's concave down, so the second derivative is less than 0, and then it's concave up to the right, and so right there, second derivative is equal to 0. Now again, notice this is different than saying the second derivative is equal to 0 on an entire interval. That's going to be a line. At a single point is different, especially when the curvature exists and it's positive or negative on either side. All right, right here, this is concave up to the left, concave down to the right. The function is defined at x equals p. Is p an inflection value? The definition was, if the function exists there, does it? Yes, and there's a sign change in the second derivative. We have a concave up, so the second derivative is positive. And then we have a concave down, so the second derivative is negative. And the function is bless you defined there. You didn't sneeze, but bless you anyway. I have a hair trigger on benedictions. It is, in fact, an inflection value. It is an inflection value. But my question now is, what is the value of the second derivative at p? It was 0 over here. Is it d and e? I don't know. Let's write it down and see. It looks like it is. After you write it down, it looks like it is. Maybe we should have talked about it before we wrote it down. Why would you say d and e? It's not smooth. Right? It's connected, but it's not smoothly connected. So we know it's not differentiable there, right? The first derivative doesn't exist there. Well, if the first derivative doesn't exist there, do you think the derivative of a non-existent thing is going to exist? No. No, it's not. It's not. It's not. So, the second derivative is also d and e there. But is it an inflection value? Totally. Yeah. So, we're already seeing two different possibilities where these inflection values can occur. They have to be in the domain of the function, but right now the derivative can be 0 or undefined. Man, that sounds familiar, right? Like when we're looking for local max or mins. We know it can only occur where the function is defined and the first derivative is either 0 or undefined. It's almost like we're finding critical values of f prime, huh? Keep that in mind. All right, here's one. Let's see. It's concave up to the left and concave what to the right? Up. Is that an inflection value? It's not an inflection value because the curvature didn't change there, right? F prime is greater than 0 to the left. F prime is greater than 0 to the right. What's the value of the second derivative there? D and E. So we're seeing that we're going to need to identify those x values where the second derivative is undefined because they will become possible inflection values. But just like not every critical value is a local max or min, I'm guessing not every place where the second derivative is undefined is it going to be an inflection value. It's almost like it's analogous. Huh? What did I put F prime. Yeah, it wasn't a lie on the left, but it wasn't what I wanted to say either. Thank you. I get excited sometimes. All the time. All right, so how about this one? We have concave, what on the left? Down. Let me try it. F double prime is down, so it's negative. And then on the right, it's concave up, so F double prime is positive. It went from a negative second derivative to a positive second derivative, add an x value. That must be an inflection value, yes? Why not, Wybert? What's it? The value at x. Very good. X equals p is not in the domain of the function. So it's a very important value, right? But it's not going to be an inflection value. Sweet. Okay. Here's the definition. A possible inflection value, which I abbreviate PIV, as opposed to a critical value, which is CV, of a function f is an x value in the domain, as Weber just said, right? Such that either one of the two things happens, f double prime equals 0 or f double prime equals d and e. We're going to call that a PIV. So they're like CVs, right? They're like critical values of a function f. In fact, they actually are the critical values of f prime. All right? Now, there's no other name for it. Like local max and min occur at critical values. Not every critical value is a local max or min. Inflection values are only going to occur at possible inflection values, but not every possible inflection value is an actual inflection value. So this right here, we said was not an inflection value because the graph was concave up on either side. but it will show up in our analysis. It is going to be a possible inflection value, a PIV. Make sense? Okay. Theorems, plural. A lot of theory in this section. The graph of a function can change its concavity at either a possible inflection value, where the second derivative is 0 or undefined, or at a, or at a discontinuity. The discontinuity. An inflection value can only occur at a possible inflection value, but not every possible inflection value is an inflection value. Got it? Everything we're going to be doing now with the second derivative is going to be almost identical to what we did with the first derivative. The only difference is we're not going to be talking about increasing and decreasing in local extrema. We're going to be talking about concave up, concave down, and inflection values. Okay, so it's the same thing, just one rung higher on the derivative ladder. So that's what we're going to do next. We're going to test for intervals of concavity. Just like we tested for intervals of increasing and decreasing, we're going to look to see where the graph is concave up or down. Here's the plan. We're going to find any discontinuities of the function. We're going to analyze the domain what? First, second, or never, or last? First. Identify the discontinuities. If they're not in the domain of the function, are they going to make their way into our little number line chart? Yes, they are. Yes, they are. They're not going to be inflection values, but they will be very important values, right? Okay, just like we saw up here. A graph can change its concavity on either side of a vertical asymptote. When we draw them in the number line, though, we're going to draw them as what? Dotted or dashed lines. Dashed. That's the Shakespearean way to say dashed. Identify any PIVs, possible inflection values that are in the domain, by finding where the derivative is 0 undefined. Then we're going to make a number line chart, except we're going to be using second derivative information rather than first derivative information. And just like with the other number line chart, where the second derivative is positive, the graph will be concave up like a cup. And where it's negative, it's going to be concave down like a frown. All right, now before we do it with an equation, let's practice on a graph, right? This is kind of getting your toe wet, right? Testing the water. The graph of a function f defined everywhere and given on the interval from k to a to k. I saw that and I wanted to say ak. Sorry, it's given below. Yeah, thank you. Give the possible inflection values. All right, so let's just list them. We won't do any justification here. We'll just list them from left to right. B, good. Why B? It's defined everywhere, so we don't have to get that first part. We're just looking to see where the derivative is 0 or undefined. How do you know it's B? Oh, it goes concave down to concave up. Sweet. Okay, next. C, concave up to concave down. Good. D. E. A. Oh, H. Okay, H. E. Why E? It's a possible inflection value. If you see a cusp, that's not only going to be a critical value, it's going to be a possible inflection value every time. Okay, because if it's where the derivative is undefined, the second derivative will be undefined. Not every critical value, though, is going to be a possible inflection value, though, right? Not every horizontal tangent is going to be a change in curvature, but every cusp will be. And you said H, yes, because H is defined and the curvature changes there. What about the endpoints, A and K? Are they PIVs? Well, let's see what the definition for a PIV is. The function has to be defined there, and I think the graph is defined at the endpoints, right? And either the derivative is 0 there or undefined. What do we know about the derivative at the endpoints? It will be undefined because it doesn't live on the other side. So believe it or not, they do find their way into the PIV list. Now, are they going to end up being actual inflection values? No, because to be an actual inflection value, you need a sign change in the second derivative on either side. And is there any way to test what the sign is on the other side of the endpoint? No. Okay, now we're doing part B. At each PIV, determine if they are actually inflection values. So the question is, can we remove the P from their status and just call them IVs? Well, of course, A and K we cannot. But what about B? Yes, simply because the graph changes from concave down to concave up, which later we'll say the second derivative changes from positive to negative at x equals b. How about así, señores? Sí. Muy bien, muy bien. ¿Por qué? ¿Por qué sí? Because f double prime changes from positive to negative. The graph changes from concave up to concave down. Muy bien. D. Yes or no? Sí. D. Sí, 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 sí. Sí, D. E, F, G, H, I, J, K, L, M, N, O, P. The graph changes from concave down to concave up. So we're going to say later the second derivative changes from negative. Did y'all say from negative, down like frown, negative, down, down like frown, negative, to positive? How about E? No. E is not an actual inflection value. Concave up on the left, concave down on the right. No, that would make it. Yeah. Concave up, concave up. There you go. So no, sorry, E. What about H? K's out. We already know that. What about H? Believe it or not, yeah. I mean, here's what has to happen, right? The function has to be defined there. It is, see the dot? Immediately to the left, we have values that are lower, and immediately to the right, we have values that are lower. So it is a local maximum as well, right? But not by the first derivative test. But it also is an inflection value because immediately to the left, the second derivative is positive, or the graph is concave up, and immediately to the right, the second derivative is negative because the graph is concave down. So by definition, yes, it is in fact going to be an actual inflection value. Okay, part C, list the open intervals where the function is concave up, down, or constant. Well, this should be easy. F is, and I'm going to go ahead and abbreviate now, between now and Cinco de Mayo, CC up, which is short for concave up. You could do the same except on Cinco de Mayo. Go ahead and write it out. On the intervals from, open intervals from B to C, union C to D is up. I think that's down. D to E and then E to H. Or can we just go straight from D to H, right? Well, let's think about it. It is concave up to the left and right of E. But if I say that it's concave up at E, I'm saying not only does the curvature exist, but that it's a positive number. And does the curvature exist at that point? No, because the first derivative doesn't exist, neither will the second. So for concavity, we must step over it. D comma E, union E comma H, and we're done. And then F is CC down, like a frown. Could you write like a frown on your AP exam? You could, yeah, you could. You could. That would make the graders happy, ironically. F is CC down on the intervals from A to B, union C to D, union H to K, right? All right, that wasn't too bad. Tested the waters. Pretty good. Feels pretty good. Deep enough. Temperature's right. Let's cannonball in. Right before lunch. Cannonball. All right. Important idea is to reiterate, which means to iterate again. Iterate means to repeat. So reiterate means to re-repeat. Not every PIV is an inflection value, right? Not every PIV is an inflection value. Just like not every critical value is a local max or min. See the analogy? Concavity can change at a discontinuity, such as the vertical asymptote, but it won't be an inflection point. Just like increasing, decreasing can change there. To find your PIVs, your possible inflection values, find any value in the domain such that the first derivative or second derivative is 0 or undefined, just like your critical values. And then a chart will help you determine the intervals of concavity as well as the justification for the inflection points. Just like a first derivative number line chart gives you increasing, decreasing intervals and first derivative justification. Discontinuities make their way into any number line chart. Okay, we have 4 minutes. Let's do example 4a. What's the domain of this function? All real numbers. Okay, so I want to know where it's concave up, concave down on the closed interval from 0 to 2 pi. So we're going to need the second derivative. So we got to go through the first. Here we go. Cosine. Yay. The second derivative is negative sine. Now, the number one type of possible inflection value that students forget to consider is the one where the second derivative is undefined. So we'll always consider it first. Is negative sign ever undefined? No. It's defined everywhere. So we're only going to use this equation once, so we'll go ahead and set it equal to 0. Now, if you're solving, you might multiply both sides by -1, right, to get sine of x equals 0. You must be very careful then, because when it comes back to plugging in numbers, guess what? You don't want to plug in the sine of x. That's not your full-fledged factored version of the second derivative. So you want to make sure that before you start algebraically manipulating it, you identify your full-fledged factored version of the second derivative. Okay, now it's unit circle time. Almost lunchtime, but still unit circle time. There are some values, I believe, within one rotation where sine is 0, and they are 0, pi, and 2 pi. Now, 0 and 2 pi are the endpoints of the interval, so we really don't have to consider them. So there's really only one point on the open interval, and that's pi. So now here we go. We'll make a little number line chart. X and y double prime. I would probably put a 0 over here and a 2 pi over there just to make sure that I'm not choosing a value less than pi. Because normally you might say, any number less than pi would work, like my favorite number less than pi, which is -58 pi. But that wouldn't work here, because that's less than 0. So picking some test values like, quadrantal angles, good, are kind of nice when you can get them. And we're plugging it back into here, right, sine of x? Oh, no, if you did that, you'd be getting the exact opposite of what you want. So, we got to plug them back into the full-fledged factored version, which is up here. All right, so when you plug in a pi halves, you get sine of pi halves, which is 1, times negative is negative, who cares? Don't tell me what it is. 3 pi halves, sine of 3 pi halves is -1 times another negative, makes it positive, it doesn't matter. Now we got our intervals of increasing, decreasing, or concavity. Y, bless you, is CC down like a frown on the open interval from 0 to pi. Y is CC up like a cup on the interval from pi to 2 pi. And then here's the sentence for the justification. Y has an inflection value. Did it ask for the point or the value? Because that's the difference between finding the y value or not. This has inflection value. Okay, at x equals pi, since, and you'll get used to this argument, it's very similar to the first derivative, since y double prime changes from negative to positive at x equals pi. Now, the way the sign changes for a local max or min is super important. If f prime changes from positive to negative, you have a local max. And if f prime changes from negative to positive, you have a local min. It doesn't matter how the sign changes for the second derivative to actually be an inflection value. We don't make a distinction between one or the other if it changes from concave up to concave down or vice versa. But guess what? College Board and I still require you to say how the sign changes. You can't just say since the sign of the second derivative changes at pi. Although that's really all that's needed. You must say how it changes. Now, when you get back from lunch, we're going to actually graph this and see if we couldn't have answered the calculus questions just from a little pre-cal knowledge without having to BOTC. And hopefully the results, if we could do that, should be consistent with each other, right? And then we'll trust our methods, and then all that. But there's the bell. Have a good lunch.